For centuries, alchemists sought to transmute base metals into gold. Modern physics focuses on a different objective: weaponizing the element. The goal is to use radioactive gold nanoparticles as an internal payload. If delivered directly into a tumor, they can destroy cancer cells from the inside out. Standard nanoparticle synthesis relies on toxic reducing agents and harsh chemical surfactants. These additives are effective in a lab, but dangerous to inject into a human patient. Engineering a viable medical treatment requires a method for building these particles that is completely sterile, producing radioactive nanomaterials without using standard chemical ingredients. This nuclear method simplifies the recipe to 3 primary components: a solid sheet of pure gold foil, purified water, and a beam of thermal neutrons. To ensure the process works, scientists often add a small amount of a 4th ingredient, a scavenger, to manage the volatile chemistry that follows. These components are placed inside the core of a research reactor. The synthesis takes place within this extreme, high radiation environment. Inside the core, the radiation performs 2 tasks at once. It transforms the stable gold into a radioactive isotope and simultaneously drives the chemical assembly of the nanoparticle. The reaction begins when a single thermal neutron strikes a stable gold 197 nucleus deep within the foil lattice. The nucleus captures the neutron and becomes excited, releasing prompt gamma rays to return to stability. This trigger is known as the Szilárd-Chalmers effect. To conserve momentum during gamma emission, the gold nucleus recoils, imparting roughly 100 eV of kinetic energy, which vastly exceeds the 25 eV required to break the metallic bonds, physically ejecting the newly radioactive atom out of the solid foil. Through this subatomic kick, the radioactive gold 198 leaves its solid state and enters the surrounding water. Because gold has a high atomic number of 79, it interacts with radiation far more intensely than the water. It absorbs energy and releases a massive shower of low-energy Auger electrons. These short-range Auger electrons dump their energy into the first few nanometers of water. This creates a nanoscopic dose enhancement, spiking radiation 600 times higher at the boundary. This spike shreds H2O molecules, transforming the water into highly reactive radicals. The presence of the gold foil has transformed the inert water surrounding it into a localized high-energy chemical factory. The newly ejected gold 198 enters this factory as a positively charged ion. It is immediately caught in a chemical tug-of-war between 2 different forces. Oxidizing hydroxyl radicals try to keep the gold ionic, while hydrated electrons act as powerful reducing agents. Added scavengers neutralize the oxidizers, tilting the chemical scales so the hydrated electrons win the tug-of-war, returning the gold to its metallic form. Bombarded by these electrons, the gold ion is systematically reduced. It moves from its 3+ state down to a neutral, 0-valent atom. This radiolytic reduction satisfies the final requirement for physical assembly. The water at the interface is now critically supersaturated. It is overloaded with free-floating, neutral radioactive gold atoms. These atoms begin to coalesce through a process called burst nucleation. They spontaneously lock together to form a perfectly organized nanoparticle. This assembly occurs without the need for external binders. The particles form organically, driven by the physics of the reactor environment. The chain reaction is complete. The result is a pristine radioactive nanomaterial suspended in pure water. This one-pot process replaces the multi-step chemical methods used in traditional nanotechnology. It eliminates the risk of toxic chemical contamination. The reactor itself acts as the architect. Radiation provides the force required to both create the isotope and build the material. This unique nuclear process creates a completely sterile, highly radioactive, and incredibly precise tool, specifically designed to safely enter the human bloodstream. While we have engineered the payload, the next challenge is to guide these particles to their target. In our next episode, we look at how doctors aim this nuclear weapon at a tumor.